Hello students, in this session we'll be discussing preparation of some heterocycles. 5-membered as well as a 6-membered heterocycle is what we'll be discussing. We'll be discussing the synthesis of furan, thiophene, okay, and pyrole. These are the 5-membered heterocycles, as well as we'll be discussing the synthesis of a 6-membered heterocycle, that is pyridine. The synthesis of furan, thiophene as well as pyrole, okay, these compounds heterocycles can be prepared from 1,4 diketones. This can be prepared from 1,4 diketones. So you know what are ketones? Ketones are the compounds that contains C double bond O group. These are called as ketones, where both these positions should be an alkyl group. Okay, if one is hydrogen, then it will be an aldehyde. So both should be an alkyl part only. Because carbon valency is 4, it has double bonded, it is doubly bonded to oxygen. So the remaining two should be alkyl. Now, diketones. Diketones means there will be two ketonic group. There will be two ketonic group. 1,4. That is, if there is a ketone at this position, so if I consider this as first carbon, then on the fourth carbon there will be another ketonic group. Okay, if I want to give an example for this can be a 1,4 diketone. See, C double bond O, some CH2 molecule, CH2 group, CH2 group, C double bond O. Okay, now here an alkyl chain, whatever it may be, CH3, C2H5, whatever it is, they may be same or they may not be same. No problem with that. Now R dash is what I can write. See, this is the first ketonic group. So 1, 2, 3, 4. On the fourth carbon there is another ketonic group. So these compounds are called as 1,4 diketones. Okay, the synthesis of furan, thiophene as well as pyrole can be achieved from this 1,4 diketones. So because these are all 5-member heterocycles, so since they are 5-member heterocycles, what happens is they contain 4 carbon. See, furan contains 4 carbon and 1 oxygen. This is furan, right? Thiophene contains 4 carbon and 1 sulfur, right? Whereas pyrrole, it is a heterocycle with of nitrogen, a 5-member heterocycle. When I say a 5-member heterocycle, 4 carbon and 1 nitrogen, 4 carbon and 1 sulfur, 4 carbon and 1 oxygen. So we require a precursor or a starting material which contains 4 carbon. So this is the best one. That's why we take 1,4 diketone is what we take. Okay, if I want to synthesize furan, I require oxygen. Oxygen is already present here. So if I want to synthesize thiophene, I require sulfur. So I will be adding some compounds containing sulfur to this. If I want pyrrole, so I require nitrogen. So what I can do is I will be adding some compounds containing a compound containing nitrogen. We'll deal with that later, what compound we are going to add. So the synthesis of furan, thiophene or pyrrole, we can carry out the synthesis by using by 1,4 diketones. So these are 1,4 diketones. Okay, let us I will just start with the synthesis of the furan molecule. So 1,4 diketone. Okay, now this CH2, yeah, CH2, I'll just write it like this. C double bond O, the R group, C double bond O, the R group. So this is how I written is 1, 2, 3, 4. First ketonic group, second ketonic group, that is 1,4 position. So these are 1,4 diketones. So what I want to prepare this molecule. I want to prepare furan. So I require 4 carbon and 1 oxygen. So there are 4 carbon here. 1, 2, 3, 4, and there is an oxygen here. Okay, now only thing that I should do is this oxygen will attack here. Why this oxygen will attack here? Because it contains lone pair of electron and this carries a positive charge because oxygen is more electronegative. So hence this will attack here. Okay, this double bonded carbon double bonded oxygen, these electrons will attack here now. So this can be brought about in presence of H2SO4, or even you can use P2O5. So sulfuric acid or P2O5 are the dehydrating agents. They are the dehydrating agents. We want dehydration to be, we require only dehydration only. So what happens is this oxygen attacks this carbon. Okay, this double bonded oxygen becomes single bonded O minus. Actually, initially it gets protonated because of H2SO4. H2SO4 is a proton donor, so it becomes H plus here. Okay, then this oxygen attacks, so double bond O gets converted into single bond OH. Then what happens? From here, the loss of proton takes place, and H plus from here, and OH goes from here. So loss of water takes place, and you end up in getting this compound, that is the furan molecule. Okay, simple dehydration of this 1,4-diketones using H2SO4 will give you a furan molecule, right? So this furan derivatives, this is prepared simply by dehydrating 1,4-diketones with P2O5 or concentrated H2SO4. Okay, hope this is clear. Right now, let us see the synthesis of thiophene molecule and the pyrole molecule. See, one thing you should remember is, if you want to synthesize thiophene, we require sulfur here. So 1,4-diketones does not contain sulfur. Hence, we need to add compounds containing sulfur. If you want to synthesize pyrole, you should add compound containing nitrogen. Right? Let us see the synthesis of, this is the synthesis of furan. Let us go for the synthesis of thiophene as well as pyrole. Okay, now synthesis of thiophene. This is the thiophene molecule. So thiophene also can be prepared from 1,4-diketones. Okay, it can be prepared. There are other methods also, but 1,4-di preparation from 1,4-diketone is there for a syllabus. So the preparation of thiophene, let us see the preparation of thiophene from 1,4-diketones. This preparation is also referred as Pal-Nor synthesis. It is called as Pal-Nor synthesis. Okay. Now, see, 1,4-diketones. I will take 1,4-diketone. CH2, CH2, C, the R group, double bond O, R group, and the double bond O. So this is R, or R dash you can take it as. So this is 1,4-diketones, 1,4-diketone. So what we want is here, we want this thiophene. So that means I want sulfur to be introduced here. So what is that is, this molecule is treated with P2S5, phosphorus pentasulfide, at 100 degrees Celsius. So what happens is, initially this C double bond O gets replaced by sulfur. It becomes C double bond S. This sulfur attacks this carbon and the dehydration takes place. And it is supported by the temperature that is here. So you get this molecule. Double bond and the R groups that are already present here. So you get dialkyl thiophene is what you get. Okay. This is the same as the synthesis of furan, provided in furan we don't require a sulfur, hence we use dehydrating agents like phosphorus pentaoxide or H2SO4. But since we require a sulfur here, so we should add a compound containing sulfur. So we add P2S5. So C double bond O gets replaced by C S, and that sulfur attacks this carbon, and the loss of water takes place, resulting in the formation of thiophene. Okay, let us go for synthesis of pyrole. Let us go for the pyrole. See, pyrole is a 5-membered heterocycle containing nitrogen. This is the pyrole molecule. Okay, pyrole can be prepared from 1,4-diketones. You can prepare pyrole from 1,4-diketones, provided we need to add a nitrogen containing compounds. So if we add a primary amine, the synthesis can be done, right? So 1,4-diketone, I will take 1,4-diketone, CH2, CH2, C double bond OR, this C double bond OR. This is 1,4-diketone. So this is 1,4-diketone. So this 1,4-diketone, we are trying to synthesize pyrole. So what pyrole contains? Pyrole contains a nitrogen. Hence, if this is treated with a primary amine, I will call this as R1, I will call this as R2, just to distinguish. If it is treated with a primary amine, so what happens is here, this nitrogen contains lone pair of electron. So this nitrogen attacks this carbon. Okay, single bond O, double bond O gets converted into OH. Right? So we have a carbon nitrogen bond. Again, that nitrogen will attack this carbon. So this nitrogen gets attached to both this carbon. Okay, it gets attached to both this carbon. You end up in getting this compound. As usual, R, R dash, this is R2. This is what you get. Okay, this synthesis is also referred as a Pal-Knorr synthesis only. See what actually happens. This nitrogen attacks this carbon and forms a bond. Okay, double bond O gets converted into OH, and the same nitrogen attacks this carbon to form double bond O gets converted to OH. Then loss of water takes place, hydrogen and OH from here, resulting in the formation of a double bond. So this is how the pyrole is synthesized. So see, these 5-membered heterocycles, that is thiophene, pyrole as well as furan, can be synthesized from 1,4-diketones. 1,4-diketones. Okay, so let us summarize this, all the three that we have discussed so far. See, if you take 1,4-diketone, so this is 1,4-diketone, CH2, CH2, C double bond O, R, I will take it as, I will is C double bond O, R dash. Okay, so this is 1,4-diketones. So if you treat this with phosphorus pentoxide or H2SO4, phosphorus pentoxide or H2SO4, you get thiofuran. If you treat this with phosphorus pentasulfide, you get thiophene. If you treat with this amine molecule, so what happens is you get pyrole. Okay, so P2O5 dehydration takes place and you get this compound. This compound R dash is what you get. Here first double bond O gets converted to double bond S, and that sulfur attacks. So sulfur will be introduced in the ring. Sulfur will be introduced in the ring. So you get this compound. Right? If we add amine, nitrogen will attack this carbon, and that the same nitrogen will attack this carbon, and the loss of water molecules takes place, resulting in the formation of a pyrole compound. Pyrole. R dash, we can take this as R2. R2 is what we get. So furan, thiophene as well as pyrole can be synthesized from 1,4-diketones. Okay, now let us see the synthesis of pyridine. Okay, so students, synthesis of pyridine, this synthesis is also referred as hard synthesis. Okay, so Pyridine can be prepared from beta ketoesters. So let us see what is this pyridine. This is a pyridine molecule, right? Hope you know this because we have discussed the aromaticity about the pyridine, right? So this is a pyridine molecule. This is a 6-member heterocycle. So pyridine can be synthesized beta ketoesters or beta carbonyl compounds on condensation with aldehyde and ammonia yields a dihydropyridine derivative, which on oxidation with nitric acid yields a pyridine derivative. Okay, what is this beta ketoesters? So these are the compounds that contain a ketonic group at the beta position of an ester. See, what is an ester? You know this C double bond O group is an ester. This will be an IR group. So the adjacent carbon is called as an alpha carbon and the next carbon is called as a beta carbon. If there is a ketonic group here, such compounds are called as beta ketoesters. We call this as beta ketoesters or beta dicarbonyl compounds also, no problem with that. C double bond O group, C, it may be a dicarbonyl compounds. So if they are beta ketoesters, carbonyl is C double bond O group. So if there is an R group also, no problem. So this is alpha and this is beta. So beta ketoesters or beta dicarbonyl compounds on condensation with aldehyde and ammonia yields a dihydropyridine derivative, which on oxidation with nitric acid is pyridine. Okay, so the beta ketoesters that is used for synthesis here is ethyl acetoacetate. Really, ethyl acetoacetate. So two molecules of ethyl acetoacetate gets condensed. One molecule gets condensed with an aldehyde, other one gets condensed with an ammonia to form an intermediate. That intermediate react to form a dihydropyridine derivative. Okay, let us see what is first ethyl acetoacetate. Ethyl acetoacetate is a beta ketoester, that is CH3 C double bond O CH2 C double bond O O C2H5. What is it? So this is ethyl acetoacetate. We call this as ethyl acetoacetate. Okay, or referred as beta ketoester. Ethyl acetoacetate or a beta ketoester. So this, when treated with an aldehyde is CH3CHO acetaldehyde and ammonia. So what happens is one molecule gets condensed with this aldehyde, another molecule gets condensed with ammonia to form an intermediate. Those two intermediate they react to form another intermediate, which on oxidation will give you pyridine molecule. Okay, so what you should remember is two molecules of this ethyl acetoacetate, one molecule of this acetaldehyde and one molecule of ammonia, they undergo condensation. Okay, this synthesis is called as Hans synthesis of pyridine. Okay, so only what you require is you require what is the intermediate that you are going to get here. Okay, that is what you should remember. So but what I will do is I will tell you how the intermediate is formed so that you will have an idea regarding this, and then I can write the intermediate easily, right? Let us see. Yeah. So first I will write this ethyl acetoacetate molecule in this fashion, right? See, C2H5 O, okay, C double bond O. Okay, this is what I am writing. Okay, C2H5O, C double bond O, the CH2 here, C double bond O CH3. Okay, ethyl acetate molecule. Okay, CH3 C double bond O, CH2 C double bond O, OC2H5. Another molecule I will write, same, C double bond O, OC2H5. Okay, then CH2 C double bond O CH3. This is another ethyl acetate molecule, right? Then acetaldehyde and ammonia. Then we have acetaldehyde molecule, CH3 CHO molecule. Okay, so what happens is this aldehyde molecule gets condensed with one aldehyde molecule will condense with one is ethyl acetate. This ethyl acetate gets condensed with another ammonia molecule. So ammonia and ethyl acetate gets condensed. So this nitrogen attacks this carbon and forms a bond. So this aldehyde is generally CH3 C double bond OH, right? CH3 C double bond OH is there. So what happens is this carbon, okay, this carbon will form bond with this carbon double bond O. So it will form one intermediate, this will form another intermediate. Those two condense with each other. Okay, I will write the exact structure of that intermediate so that we'll have an idea, and then we'll come back to this. Right now, so students, first the intermediate that I am going to write, it is C2H5 O C double bond O CH2 C double bond O CH3. Right, this is the molecule. Right, now another molecule, that is CH2 C double bond O CH3 C double bond O C double bond O OC2H5. This is another ethyl acetate molecule that I had written. Now what happens is we have ammonia, right, NH3, right, we have acetaldehyde, CH3 CHO, we have CH3 CHO. This is what we have, right? So what happens is this ammonia attacks this carbon and forms a bond, a condensation product. Okay, double bond O gets converted to single bond O, then loss of water takes place, OH from here and H from here, a double bond is formed here, so condensation takes place. This hydrogen is generally acidic in nature. Okay, what happens is enolization takes place, the double bond shift here, and this carbon attacks this carbon here, and there is a condensation product here. Okay, so we'll write the condensation products. Okay, no need of remembering these things. I want to tell you how we get the intermediate, that's what. Right, so what we get is the same molecule, C double bond O O C2H5, right? So nitrogen has attacked here, double bond gets converted into single bond OH, the loss of hydrogen and OH takes place, so hence this carbon, that is CH, forms a double bond, NH2. This is the intermediate form from this condensation. Now this carbon oxygen gets condensed, so you get loss of water takes place, two hydrogen from here, one oxygen, so it forms double bonded here, right? You get this compound CH3 as usual, CH, these two are getting condensed, C, the remaining as usual, C double bond O CH3 C double bond O OC2H5, right? So these are the two intermediate that are formed. One is formed by condensation of one ethyl acetate with ammonia, another one by another ethyl acetate with acetaldehyde. Right. Then what happens? The reaction between these two takes place. This nitrogen attacks this carbon. Okay, this double bonded, that is, attacks this. So there will be a formation of a ring. So how many membered ring? 6 membered. Look at this. 1, 2, 3 nitrogen, 4 carbon, 5 carbon, and this 6 carbon. So you get this ring. Just look at the ring, students. So we have a 6 membered ring here with one nitrogen. We have 6 membered ring here with one nitrogen. Okay, this is what you should remember. So there will be a methyl group here, CH3, ester on both the sides, C double bond O, OC2H5, C double bond O, OC2H5, right? And the this two methyl groups here, CH3, CH3, two methyl groups here, and the two double bonds here. This double bond here, and this shift here double bond is formed. This is what I am going to get. So this is the dihydropyridine derivative that you are going to get. Dihydropyridine derivative. Okay, so you need to remember this thing. I'm telling you how to remember it. So I just told you how actually the condensation takes place. One acetate, ethyl acetate reacts with ammonia, another ethyl acetate reacts with acetaldehyde to form an intermediate that react to form a 6-membered intermediate. Okay, no need of remembering these things. You get confused with that. So I will tell you how to implement the points. That's all. Okay, what you should do is you should take two ethyl acetate molecules, because two ethyl acetate molecules are required for this reaction. So we are going to take two ethyl acetate molecules. You know what is an ethyl acetate molecule? Well, it is an ester, right? So it will be CH3, C double bond O, CH2, C double bond O, OC2H5. So two molecules of ethyl acetate, then one acetaldehyde molecule plus one ammonia molecule. They undergo condensation. This is only the thing that you should remember. Two ethyl acetate molecule, one acetaldehyde, and one ammonia molecule. They undergo condensation to form a dihydropyridine derivative. Okay, it will be a 6-membered dihydropyridine derivative, right? This is how you should remember, right? A pyridine derivative. So here there will be a methyl group. There will be a methyl group. There will be an ester part here. There will be an ester part, C double bond O, OC2H5. There will be ester here, C double bond O, OC2H5. Okay, there will be a methyl here, as well as there will be a methyl here. Okay, this is what you are going to get, right? Now, so this is how we should write it, right? A 6-membered. This on oxidation with HNO3. If we carry out oxidation using HNO3, it undergoes oxidation to form pyridine. Okay, so this is what you get. So as usual, the groups are as usual. CH3, a methyl group, an ester part, C double bond O, OC2H5, a methyl group, then this C double bond O, OC2H5. And this is what you get. Okay, so now, so this is the pyridine that you are going to get. So if you heat this molecule, in presence of a base OH minus and calcium oxide, okay, so a decarboxylation will take place, CO2, loss of CO2, and you end up in getting this molecule. CH3, CH3, CH3. This is 2,4,6 trimethyl pyridine is what you are going to get. Okay, see students, this is what you should remember. Two molecules of ethyl acetate, one ammonia molecule and one acetaldehyde molecule. They undergo condensation to form a pyridine compound. So this one, it will be a 6-membered with nitrogen with 3 methyl groups and 2 ester part here. C double bond O, OC2H5, C double bond O, OC2H5. When adding HNO3, it undergoes oxidation to form pyridine. This is a dihydropyridine. This is pyridine derivative, right? Then, in presence of NaOH or OH minus calcium oxide, if you heat it, so you get 2,4,6 trimethyl pyridine. Okay, students. In this session, we have discussed the synthesis of furan, thiophene, okay, pyrole as well as pyridine. So this is the synthesis of pyridine, and this synthesis is called as the Hans synthesis. Okay. In next session, we will be discussing about the reactions of these heterocycles. Thank you.